The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Greetings, and welcome to 507 Biochemistry Online. I'm Dr. Bogdan Fedelesh. Let's metabolize some problems. I have a good problem for you today. This is problem 1 from problem set 9. It is a problem in which we're going to calculate how much energy we get from metabolizing a molecule of fat, more specifically, a molecule of triacylglycerol. Here is a structural representation of the triacylglycerol. Recognize the glycerol molecule in the middle here that it's holding together 3 fatty acids. Now notice I picked a short chain fatty acid, a long chain fatty acid, and a fatty acid that actually has a double bond. All right, now when this molecule gets metabolized, it's going to be acted upon by an enzyme called the lipase. It's going to hydrolyze the molecule into its constituents. Obviously, the lipase is going to use water molecules, and it's going to break it down into glycerol, shown here. Glycerol, then this fatty acid that has 2,4,6 C6 fatty acid. This fatty acid has 2, 4, 6, 8, 10, 12, 14, 16 C16 fatty acid. And this one, it's a unsaturated fatty acid, has a double bond, and if you count the carbons, it should add up to 15 carbons. So not only it has a double bond, but also it's an odd-numbered fatty acid. In order to figure out how much energy we can get from this one molecule of fat, we will look at how much energy we get from each one of these constituents, namely the glycerol and the 3 fatty acids, and calculate what is the maximum amount of ATP we can generate when we metabolize each one of these molecules completely to CO2 and water. In order to keep track of how much energy we get from each of the molecules, let's make a handy table right here. So I'm going to put glycerol and the C6 fatty acid, the C16 fatty acid, and C15 fatty acid. All right, and each one of these, we're going to follow the metabolism and see how much ATP we're going to need to put in or generate. Also the redox cofactors NADH or FADH2. Also for fatty acids, we're going to be dealing with beta oxidation. And pretty much every single molecule, when it's going to be burned completely, it's going to generate first acetyl-CoA. All right, and here we're going to tally up the total amount of ATP for each one of them, and then we're going to tally up for the entire molecule. So let's start with the glycerol molecule. Now, if you have watched the problem set 7, you might recognize the following pathway. As we just discussed, triacylglyceride can be hydrolyzed to form glycerol, right? And the glycerol then is first phosphorylated by glycerol kinase and oxidized by glycerol phosphate dehydrogenase to generate dihydroacetone phosphate, which can then enter the glycolysis and follow glycolysis all the way to pyruvate and then acetyl-CoA. From then, acetyl-CoA can go into the TCA cycle. So now, let's tally up how much energy we can get from one molecule of glycerol. So let's take a look specifically at the steps where we're generating ATP or generating redox cofactors such as NADH or FADH2. First, we need to put in ATP in the glycerol kinase, but we're going to get back 1 ATP in the phosphoglycerate kinase step and 1 ATP in the pyruvate kinase step. So the net ATP formation is 1. Now, in the glycolysis, we're also going to generate 1 NADH and the pyruvate dehydrogenase another NADH, and the glycerol 3-phosphate dehydrogenase will generate also an NADH. Now, keep in mind this NADH is going to be outside the mitochondria, so we're going to have to use a shuttle to bring it in, but we're considering that we're using an efficient shuttle that gives us the full amount of energy for this NADH. So once again, a total, it's going to be 3 molecules of NADH. So going back to our table, we said the glycerol is going to give us a net 1 molecule of ATP, 3 molecules of NADH. There's going to be no FADH2, no beta oxidation, and we're going to get a 1 molecule of acetyl-CoA. As you've seen by this point many times, acetyl-CoA will enter the TCA cycle where it's going to be completely oxidized to 2 CO2 molecules, and in the process is going to generate the equivalent of 12 ATPs. Let's take a look where those are coming from. Here is a schematic of the TCA cycle, and one acetyl-CoA molecule comes in, and it's going to generate 1, 2, 3 molecules of NADH, 1 molecule of FADH2, and 1 molecule of GTP. Now, if we keep in mind that for every FADH2s, we generate about 2 ATPs, and for every NADH, we generate 3 ATPs, that's a total of 3 times 3 is 9, plus 2, 11, plus a GTP is equivalent to an ATP. So that's about 12 molecules of ATP per molecule of acetyl-CoA that enters the TCA cycle. So now let's tally up how much energy we can get from 1 molecule of glycerol. So we know we get 1 ATP, 3 NADHs. Now each NADH is going to give us 3 molecules of ATP. Now FADH2, we know these give 2 molecules of ATP. We don't have any. Beta oxidation, we're going to be talking more about fatty acids. And acetyl-CoA, we just talked about, we get 12 molecules of ATP per acetyl-CoA. So the total here is 12 plus 9 plus 1. That's going to be 22 ATPs for 1 molecule of glycerol. Now let's talk about the fatty acids. In order to metabolize them, first we need to activate them into thioesters. These are going to be thioesters formed with coenzyme A, or CoA. Here's an overview of the activation process by which fatty acids become fatty acid thioesters. Of course, this is written for the C6 fatty acid, but would occur for any other fatty acid regardless of the chain length. Now, this process is catalyzed by acyl-CoA synthetase that uses ATP to first generate this mixed anhydride with AMP. This process is called adenylation. So this activates the acid, which then reacts with coenzyme A, shown here, HS-CoA, which will generate the thioester of the fatty acid. Now, here we're using 1 molecule of ATP, but we're breaking in the alpha phosphate to generate pyrophosphate, which is then broken down into 2 inorganic phosphate. And the energy in this reaction catalyzed by inorganic pyrophosphatase drives the reaction towards the right. Now, since we're generating AMP in the second step, we need a second molecule of ATP to convert this AMP back to ADP. So overall, this process requires 2 molecules of ATP to generate 1 molecule of the fatty acid thioester. Once the fatty acid is activated into a thioester with coenzyme A, it can now undergo beta oxidation. This is a set of reactions in which the fatty acid is broken down into a shorter fatty acid and 1 molecule of acetyl-CoA. The process then can repeat over and over until the entire fatty acid is broken down into acetyl-CoA molecules. So let's take a look at how beta oxidation works. Here's an overview of the beta oxidation pathway. We're starting with a fatty acyl-CoA thioester that has N carbons, and by the end of the process we're going to get a thioester that has N-2 carbons, and the remaining 2 carbons are going to be in the form of acetyl-CoA. Now, this beta oxidation involves 4 steps. In the first step, we're going to use a dehydrogenase to oxidize this single bond between the alpha and the beta carbons and make a trans double bond. So this is the alpha carbon, this is the beta carbon. So these fatty acyl-CoA dehydrogenases there are actually several of them, and they have different specificity for short, medium, long, and very long chain fatty acyl-CoAs. But regardless, there will be some dehydrogenase to act on any length fatty acyl-CoA and introduce this trans double bond. In the next step, we add one water molecule to generate a beta hydroxyl acyl-CoA, which is subsequently oxidized to generate a beta keto acyl-CoA. In this oxidation, we're going to use NAD, generating one molecule of NADH. Finally, the thiolase, or beta keto acyl thiolase, is going to break down this bond between the alpha and beta carbons in a reverse Claisen reaction to generate one molecule of acetyl-CoA and the remainder of the fatty acid as another thioester. So one round of beta oxidation is going to generate one molecule of FADH2 and one molecule of NADH, as well as one molecule of acetyl-CoA. Now, let's update our table with the information we just learned. So, as we just said, for every fatty acid, we need to expand 2 molecules of ATP to transform them into the thioesters. That's why I put here -2 for each one of the 3 fatty acids. We also learned that in beta oxidation, we generate one molecule of FADH2 and one molecule of NADH. So for every beta oxidation, we generate the equivalent of 5 ATP. Now we're ready to calculate how much energy we can get from each of the 3 fatty acids in our problem. Now, for the C6 fatty acid, let's represent it here. We discussed we're going to activate it. We're going to need to use 2 ATP molecules and coenzyme A. We're going to form the thioester. And then we're going to do beta oxidation. Now, for a fatty acid that has 6 carbons, we're going to do the beta oxidation, and the molecule is going to cleave there. And we're going to do it one more time. The molecule is going to be cleaved there. So we're going to do 2 rounds of beta oxidation. And each one of these 2 carbons is going to become an acetyl-CoA. So we're going to generate 3 acetyl-CoAs. Now, similarly, for the C16 fatty acid, 2, 4, 6, 8, 10, 12, 14, 16. All right, it's going to first activate it, 2 molecules of ATP and coenzyme A to form the thioester with 16 carbons, and this will undergo beta oxidation, and we're going to do it 1, 2, 3, 4, 5, 6, 7 times. Okay, so 7 rounds of beta oxidation. It's going to generate 8 molecules of acetyl-CoA. Now let's go back and put in all this information into our table. So for the C6 fatty acid, we expended 2 molecules of ATP to activate it, and then we did 2 rounds of beta oxidation, and we generated 3 molecules of acetyl-CoA. For the C16 fatty acid, again, we activated, then we did 7 rounds of beta oxidation, and we generated 8 molecules of acetyl-CoA. So for the C6 fatty acid, we have a grand total of 3 times 12 is 36, plus 2 times 5, 10, that's 46, minus 2, it's 44 molecules of ATP. For the C16 fatty acid, well, 8 times 12 is 96, plus 35, minus 2, that's 129 molecules of ATP. Now, the C15 fatty acid is going to be a little bit more complicated because on one hand, it has a double bond, so we need to figure out how to deal with that. On the other hand, it's an odd chain fatty acid. And as you imagine, the beta oxidation breaks off 2 carbons at a time, So the last time we do beta oxidation, we're going to be left with 3 carbons. That's called propionyl-CoA, and we have to figure out what to do with that. Just as with the other fatty acids, the C15 fatty acid is going to need to be activated into a thioester with CoA. So this is going to cost 2 ATP molecules, and of course we need to add the CoA. And now this is the thioester of our C15 fatty acid. Now, since the double bond is pretty far away from the business end of the molecule, we can do a number of rounds of beta oxidation. In fact, we can do beta oxidation once, twice. So 2 rounds of beta oxidation is going to give us to this molecule. 2 rounds beta oxidation. Okay, in each one of these rounds, we're going to generate 1 molecule of acetyl-CoA, so 2 acetyl-CoA. So we get this fatty acid thioester, which contains a beta-gamma double bond. Now it turns out there's an enzyme that can isomerize this double bond into an alpha-beta double bond. So this is what is going to happen next. The double bond moves from the beta-gamma to the alpha-beta. Now this looks a lot like an intermediate in the beta oxidation. Once again, this reaction is catalyzed by an isomerase. And this alpha-beta unsaturated thioester can continue in a manner similar to the beta oxidation. So first is going to add water to form a hydroxyl here at the beta position. Then that hydroxyl is going to oxidize to form a keto group. And the thiolase is going to generate acetyl-CoA and another thioester shown here. So from here, we're going to generate 1 molecule of NADH and 1 molecule of acetyl-CoA. All right, now this is a thioester of a completely saturated fatty acid. Now, of course, it's still odd chain, so we have 1, 6, 7, 8, 9 carbons. So we can do beta oxidation actually 3 times. So 3 rounds of beta oxidation, and it's going to take us to 3 molecules of acetyl-CoA, and the last portion of the molecule is going to be this molecule, which we call propionyl-CoA. It's 3 carbons thioester. So far, we have generated 2, 3, and another 3 here, 6 molecules of acetyl-CoA. And we've done 2, and another 3, 5 rounds of beta oxidation. And we also generated an additional NADH molecule. So now let's update our table with this information, and then we're going to figure out what happens to propionyl-CoA. As we just discussed, the C15 fatty acid is going to get activated, so we need 2 ATPs there. Then it's going to undergo 5 rounds of beta oxidation, and we generated a total of 6 molecules of acetyl-CoA and 1 additional molecule of NADH. Let's now take a look at propionyl-CoA and see how we metabolize it and how much energy we can generate from it. It turns out the first step is to expand from a 3-carbon molecule to a 4-carbon molecule. And this happens by adding 1 CO2. Of course, this process will require the expense of an ATP molecule. We generate this methylmalonyl-CoA, which is a branched 4-carbon chain molecule. And another enzyme, racemase, is going to interconvert the stereocenter from the S configuration to the R configuration. Finally, this methylmalonyl-CoA is going to undergo a rearrangement of the groups to generate a linear molecule, succinyl-CoA. Now, this is one of the most fascinating transformations in the whole biochemistry, and involves an enzyme called methylmalonyl-CoA mutase, which requires cobalamin, or the coenzyme derived from vitamin B12. This unusual transformation, catalyzed by the methylmalonyl-CoA mutase, the enzyme that requires vitamin B12 cofactor, is fascinating because it involves a carbon skeletal rearrangement of the molecule. And this reaction occurs via a radical mechanism. The radical is obtained by breaking a carbon-metal bond. In this case, it's a carbon-cobalt bond. Now, succinyl-CoA is a familiar molecule. You've encountered it in the TCA cycle. However, we cannot use the TCA cycle directly to completely metabolize succinyl-CoA, as all the intermediates in the TCA cycle are in fact in catalytic amounts. So we're going to use just part of the TCA cycle to generate a molecule malate, which then can be converted into pyruvate. And pyruvate can then generate acetyl-CoA to re-enter the TCA cycle and be completely metabolized. Here is the TCA cycle to refresh your memory. And this is succinyl-CoA that we can generate from the methylmalonyl-CoA mutase. Now, as we said, succinyl-CoA is going to be converted to malate. Malate can then escape the mitochondria and continue its transformation towards pyruvate. So in this process, succinyl-CoA is going to generate one molecule of GTP to form succinate. Then succinate to fumarate is going to give us one more molecule of FADH2. Then malate will escape the mitochondria. So to summarize what happens in the TCA cycle, succinyl-CoA is going to give us a molecule of GTP and then one more molecule of FADH2. And it's going to make it to malate, and then malate is going to be converted to pyruvate using the malic enzyme. Now, this is an oxidation and decarboxylation that happens in one step. For the oxidation, we're going to need NADP instead of the usual NAD. So we're going to generate one molecule of NADPH. Now, for the purpose of this problem, we're going to treat NADPH as equivalent to NADH. So malate, via the malic enzyme, we're going to form pyruvate, and then pyruvate in the pyruvate dehydrogenase, we're going to lose one CO2 and form acetyl-CoA. In the process, we'll also generate one more NADH, and now acetyl-CoA can re-enter the TCA cycle and be completely metabolized, generating in the process about 12 ATP equivalents. So now let's go back and update our table with all this information that we found out about propionyl-CoA. So as we said, propionyl-CoA required first the loss of another ATP to activate it to form the methylmalonyl-CoA. But then methylmalonyl-CoA converted to succinyl-CoA. Succinyl-CoA generated one molecule of GTP. So we're going to put +1 back here. Now, then we're going to get one molecule of FADH2 in the generating succinate, going from succinate to fumarate. And then we're going to generate two more molecules of NADH, one at the malic enzyme step and one at the pyruvate dehydrogenase step. So we're going to be +2 here. And of course, in the end, we get one more molecule of acetyl-CoA as well. So now we have a total of 7 molecules of acetyl-CoA, 5 rounds of beta oxidation, 1 FADH2, 3 NADHs, and at a loss of 2 ATPs. So this totals up to 118 ATPs for the C15 fatty acid. Now, we can tally the entire ATP yield of a molecule of fat of this triacyl glyceride, and that's going to be 313 molecules of ATP. Now, that's a lot of energy from one single molecule of fat. Now, this problem has an additional question, and it asked us to contrast how much energy we get from a 6-carbon fatty acid and compare that to how much energy we get from one molecule of glucose, which also has 6 carbons. Let's take a look at our table here. The 6-carbon fatty acid generates about 44 molecules of ATP when completely oxidized. By contrast, one molecule of glucose would generate only about 34 to 36 molecules of ATP. Right? If you want to follow the same analysis that we did here, remember glucose will we need to spend 2 molecules of ATP to activate it, but then we're going to generate 4 molecules of ATP going to pyruvate. And then there's going to be 2 molecules of NADH generated, one at the GAPDH step, one at the pyruvate dehydrogenase step, and finally we're going to generate 2 molecules of acetyl-CoA. So the total is going to be 2 times 12 is 24, plus 4 times 3 is 12, that's 36, plus 2 is 38. All right. So as you guys can see, the C6 fatty acid generates actually more ATP than 1 molecule of glucose. And that's probably reasonable because the C6 fatty acid has a lot more CH bonds. In other words, the carbons are more reduced. In glucose, we have a lot of hydroxyls, so the carbons are in slightly higher oxidation state. Therefore, there's less energy generated total. Of course, 1 molecule of glucose pales in comparison with 1 molecule of fat, which has like hundreds of ATP generated, as we saw in part A of this problem. Well, that sums up this problem. I hope it helped you realize why fats or triacylglycerides are so much more energy dense than other nutrients such as sugars or amino acids.